Anybody want to share? Sean? That'll do it. So your logic wasn't so bad. Even integers will do it. If I take, it's a group, an abelian under plus. Multiplication does all we need it to. It's distributive, it's associative, it's got closure, and it's commutative under multiplication. But the only hope of having a multiplicative identity would be if 1 was in there, and 1's not even. So it's a commutative ring that doesn't have an identity. You know I'm going to ask this next. What about something in there? It's a ring with identity, but not commutative. Doubt yourself!
Yeah, it's done. Yeah.
Did I just pull a David Trubach? Huh?
Does have the zero. Oh no.
I learn something new every time I talk to Dr. Trubach for even 5 minutes.
Okay. What?
Two matrices commute if they have the same eigenvectors.
Mm-hmm. It's called functionally commutative. In fact, I showed you that theorem last semester. I showed you that open theorem that if you have a function, right? No, it was at the beginning of the semester, right before everybody dropped. The day before everybody dropped. If two matrices A of S and A of T functionally commute and they have constant eigenvectors, then yeah, then you can do the decomposition, right? Mm-hmm. No, it's not. No. We have a counterexample. What condition would you need to get it to be the other way? There's an extra condition, because you can find a counterexample. It's that I haven't worked on it, and I haven't had a chance to mentor someone to work on it, because I've been doing all the other stuff.
So is this like an answered question?
No.
Oh, this is not an answered question.
It's an open question.
You want non-commutative with identity.
Got it? Right. So there's a group called the special linear group of n by n matrices that have inverses, multiplicative inverses. And those matrices are determinant of those matrices are 1, so all of those are invertible, has an identity, but as you know, matrices that don't generally commute. So that's a perfect example of. No, but.
Okay. So you can take something smaller, for example.
Yeah, you could take.
Or something bigger.
Right.
Because all you need is additive, right?
So I guess I could have, I don't have it on this Venn diagram, but I could say I want something with identity that doesn't commute and doesn't have multiplicative inverses, but has, right? So I could look for that.
Because usually when you say multiplicative inverses, you apply that there's an identity to multiply to.
Yeah, but
Right. You see what I'm saying?
Right. Right. So I don't need this condition anyways, right? I don't need it. I don't need the determinant equal 1. It's this is a standard group. You could actually remove the determinant A equals 1, and you'd still have an example. So it does all the things you need it to do. Under plus, it's an abelian group. It's associative, has the distributive property under multiplication, and it even has an identity. But it's not commutative under times. So what Ryan pointed out is I don't need determinant A equals 1. So if I asked you for an example of a, not saying that I would, but I might, ask you for an example of a ring that has an identity, and is not commutative and has no multiplicative inverses, or doesn't always have a multiplicative inverse, I could just lift off that determinant A equal 1. So there's something called a zero divisor, and it messes things up. This is all about solving equations. That's what we're headed to, right? When you want to solve equations, you want to be able to cancel things. Everybody who's taught classes where students love to cancel things knows that it's really important to be able to cancel things. Sometimes people get a little too cancel happy. I taught pre-calc at 1 o'clock today. Let R be a ring. A left zero divisor is an element such that AX equals 0 for some x not 0 and x That should be A not 0. So there's a way to multiply to 0 where both of those elements are non-zero. So let me give you an example. In the ring Z6, 2 times 3 is 0. So 2 is what we call a left zero divisor, because there's two things that were not 0. When I multiplied them, they became 0. This is a critical property that you don't want in a ring if you want to solve equations. It makes it unfortunate when it happens. Similarly, I didn't put the definition up there, but 3 would be what we call a right zero divisor. A multiplicative inverse, a multiplicative inverse of an element is just like the additive inverse of an element. It's something that turns you back to 1. So for example, it's an element B such that A times B is B times A is equal to 1. So I'm loading you up with definitions. A division ring is a ring with identity, doesn't have to be commutative, where every non-zero element has a multiplicative inverse. That's SL2. And an integral domain is a commutative ring with identity that has no non-zero divisors, but it doesn't have to necessarily have multiplicative inverses. So what this has, it's commutative, it's a ring, it has an identity, no zero divisors, but it doesn't necessarily have to have multiplicative inverses. So I'm leaving it to you. I guess I gave you one of the answers. Oops. Did a David True batch. Find an example of a true division ring, a ring that's not commutative, but where every non-zero element has a multiplicative inverse.
When is quiz 5?
It's this week take home at the beginning of the period I explained. Or quiz 4, quiz 4. It's quiz 4. I shifted right to the 1. Say it again? What about it? I had a typo in there. So the definition's right here. This should be A not 0. For some x not 0, A not 0. I don't know what I was thinking right here. X not 0 and an A not 0. So two non-zero elements multiplied up to be 0. Like in Z6, 2 times 3 is equal to 0. And I think that you guys probably talked about this in undergrad classes at some length. You know, you talked about rings like Z4, where you had zero divisors, and then prime rings like ZP, Z3, Z5. Those have no zero divisors. So it depends on what quality of undergrad class you had. I feel like in an undergrad class we beat this to death. We talk about ZP and ZN, where N is composite, for a great length, and you do a lot of computations on those for a long time, I feel like anyways. So if you didn't have that, or it's been a while since you had that, just go through some of these computations and fill in the gaps. You just have to compute a few of them to see what it looks like. So this is quiz 4. Find an example of a true integral domain. That means you're looking for a commutative ring with an identity, but no zero divisors, but doesn't include multiplicative inverses, right? So everything's there except the inverses. By the way, if you haven't talked to someone who's had me before, this test start looking with the front page ends up being a bunch of these examples asking you for them. So it's a good idea, and the comps have always had them since I've been writing them. Where just give me an example of something that's here. Give me an example of something that's here. Give me an example of something that's here. So I ask you those questions. So these questions that you're seeing right now, they will be on the exam. And if you're taking the comps, they will be on the comps. The big one is the field. A field is cool because it's an abelian group under plus, and the non-zero elements form an abelian group under times, and the distributive law holds. there's a series of books by this guy named Jacobson, and he's a algebraist. Horrible to read. Talk about notation. Oh my God. I think he's used every Hebrew letter in there, every Greek letter in there, and then subscripted them. So it's really, really tough to get through. But what's nice about the Jacobson books is it really shows you this build-up of you start with groups, and you understand that group structure. You have everything in that group structure. You can cancel. Everything about solving equations is in that group structure. And then you build and build until you get to this, that the field is everything. That's why we work on fields. In fact, you don't really work on any field but R for a long, long time. So that's the field you're familiar with. But that's why we work over the field R. Some of the professors probably use complex numbers as their field. So I was taught Hilbert spaces entirely over complex numbers. My field was never R. My field was C. That's another field. But you could do everything that you did for real numbers on Z2. That's a field. You can do all your vector space theory on Z2, over Z2. So here's an example. ZP for P prime is a finite field. It's a field and it's also finite. Do we have a property that will guarantee us that the cross product will yield a field? Can you fill in this blank, that if this, then Zn cross Zm is going to be a field? Just work some examples and see if you can get something to work. You can fill in this blank here. So it's easy to remember the definition of field. Now you have it in your head. Abelian group under plus, non-zero elements form an abelian group under times, and the distributive law holds.